Okay, so this is the last example of balancing redox reactions using the oxidation number method, and that is in a basic solution. So you'll see that we're just going to do the same steps as before, this time 1 to 7 like we did in the acidic solution. But this time we're going to add two new ones, which I'm calling 8 and 9. So step 1 is to put in our oxidation numbers for all of our atoms. Okay. Okay. And the next step is to look for the atoms that have been involved in an oxidation or in the oxidation and reduction. And these are the ones where the oxidation numbers have changed. So I look at carbon and I notice that carbon has gone from -2 to +4. So it's getting more positive. So that is an example of an oxidation. It's lost electrons. Now, how many electrons has it lost? Well, to go from -2 to +4, that is 6. So we've lost 6 electrons lost per C atom. Now we move on to the next one, hydrogen, and it's +1 as a reactant, and we don't even have any hydrogen, so we can't look in the products. Oxygen is -2 in the reactants and -2 in the products. So it's not involved in the oxidation reduction. And so we look at Mn, manganese, and we see that it has gone from +7 to +6, which is a reduction. It's getting more negative. So it has gained 1 electron. So 1 electron gained per Mn atom. And the step we always do after this is we want to look at, well, how much did the entire reactant gain or lose? So we'll take a look at this one and we see that since there's only 1 carbon and it lost 6 electrons, the whole reactant only lost 6 electrons. So 6 electrons lost per CH3OH. And if we look at MnO4, again, there's only 1 atom, 1 Mn. So the reactant has also only lost 1 electron. And now we look for our LCM. And our LCM in this case, 6 times 1 is 6. And to get to 6, we need to multiply 1 by 6. And to get to 6, we need to multiply 6 by 1. And you know by now that these numbers in the square boxes are now my coefficients for my reactants, the lowest possible coefficient. So if I write out my reaction from above, I can write in my coefficients. So this is just 1. And we don't usually write a 1, so let's assume that there's a 1 there. And for MnO4, it is a 6. So we put a 6 in there. Now we just want to make sure that we've balanced our carbon and our manganese, because those were the atoms that were involved in the oxidation and reduction, are the ones whose oxidation numbers changed. So we look over on this side, the reactant side, we have 1 carbon here, 1 carbon here, so no number required. We look at Mn, 6 Mn's here. We need to put 6 Mn's right there. Now, we've balanced our carbons, we've balanced our manganese, but the next problem is our oxygens aren't balanced. And you always go in this order. You balance your elements involved in the oxidation reduction, then oxygen, then hydrogen. So on this side, I have 24 oxygen here, plus 1 makes it 25. And on this side, I have 24 here, plus 3 makes it 28. Sorry, 27. So what I need is 2 more oxygens on this side. So I'm going to do this in steps, like I did before. So we're going to balance our O atoms. And since we have 25 on this side and 27 on this side, I need to add 2 more waters to this side. So we use waters to balance the oxygen. And that's the only thing that we're going to change here. Now, by adding the water, you have added H pluses. So we need to balance next our, we've added, sorry, H's. We need to balance our H atoms. So we can see, I'm just going to rewrite this. We have to go and check how many H atoms do I have to add to this to ensure that they're balanced on both sides. So I need to add some H pluses here to balance my H atoms. Now, the mistake that some people make is they only look at the waters. I've added 2 waters, so that means I need to put 4 H pluses right here. But that's not right. You have to be careful. You want to take into account all of the H's on the reactant side. So I've got 4 here. I'll write that down. 4 there and 4 here for a total of 8. So I need to add 8 H pluses. Now, that has balanced all the O's, all the C's, all the MN's, all the H pluses, or sorry, I should say H's, and the charges as well. So if you look at the charges, you see on this side, this adds up to -6 and -12 plus -2 -14 plus 8 is -6. So everything balances. Everything's balanced here. The only problem is this. This is an acid. And, whoops, we are in a base. If you look at the original question, look at the title of this, it says it's basic. So we cannot have acid floating around. We have to get rid of this acid. And the way you learned last year how to remove acid is you add base. And how we're going to do that is we're going to add OH minus to remove the H plus. So the only thing that we have to, that's sort of different about the OH minus is that we are going to add it to both sides. So how many H pluses or OH minuses do I need to get rid of 8 H pluses? Well, I need 8. So I'm going to have to add 8 OHs to both sides. like so. Now, we're just going to sort of clean this up a little. And what we're going to do is we're going to combine H plus and OH minus into water. Because one H plus and one OH minus will get you water. So we're not going to touch anything on the reactant side for now. And this becomes 8 waters. Now the other thing we're going to do in this step too, again, this is just sort of cleaning up the question, is you'll notice you have 8 H2Os as a product and you've got 2 H2Os as a reactant. Well, we can cancel those, and that 8 H2O will become 6 H2O. Now you could leave it here on a test, that'd be fine, but I just want to sort of clean it up, so it doesn't have things like the crossed out 2 H2Os. So just going to clean it up as a final answer. And that is your final balanced chemical equation. Now, this is a math class, so I'd be totally fine if you sort of left this as your final answer. I can follow that. And that is how we balance a redox reaction in a basic solution.